Hello, my name is Dr. Eric Gossett, Professor Emeritus of Mathematics and Computer Science at Bethel University in St. Paul, Minnesota, USA. For a second summer, the final contest of the WMI series of contests was not able to be held again due to COVID-19. Hopefully, the contest will be able to be held the summer of 2022. In the meantime, I hope you enjoy this short video about Sierpinski curves. I'm going to actually be talking about two different aspects. First of all, I need to introduce what Sierpinski curves are, and then I want to look at the very interesting idea of how do we draw these curves on a computer. In order to explain what Sierpinski curves are, we need to back up a little bit to look at some interesting things that were happening in the history of mathematics. In the late 1800s, the German mathematician Georg Cantor discovered some very unexpected mathematical ideas. Let's start with the natural numbers, 0, 1, 2, 3. Those numbers we know go on forever, so this forms an infinite set. Another infinite set you're familiar with is the set of all fractions. Mathematicians call this set the rational numbers. Here are just a few of those numbers, 1/2, 1/3, 3/4. Notice that 2 is also a rational number. We can write it as 2 over 1. 3 is a rational number, and so forth. So the natural numbers are a proper subset of the rationals. In fact, between any two natural numbers, for example, 0 and 1, there are an infinite number of rational numbers. 1/2 is between 0 and 1. 1/10 is a bit smaller. 1/100th, 1/1000th. We can keep this on forever. So there are an infinite number of rational numbers between the natural numbers, between just 0 and 1. So that makes us think that there ought to be more rational numbers than there are natural numbers. But in fact, Cantor was able to prove that these two infinite sets have exactly the same size. Now, we need to be very careful of what we mean by the same size, and to understand that, we need to understand the notion of a one-to-one correspondence. A one-to-one correspondence is a way to take two sets and arrange for each element in one set to have a unique partner in the other set, and vice versa. So we can think of a class in which the teacher arranges partners. Each boy will have exactly one girl as his partner, and each girl will have exactly one boy as her partner. And if there are no students left without a partner, then we ought to conclude that there are the same number of girls and boys. So in this set, this boy is partnered with this girl. This girl is partnered with this boy. What we notice is that every boy has exactly one girl as a partner. Every girl has exactly one boy as a partner. This one-to-one correspondence then allows us to conclude that there are the same number of boys and girls. In this classroom, there is not a one-to-one correspondence. Here is a boy that has no partner. And so we say that these two sets are not the same size. Now this seems like a lot of work to prove the size of two sets are the same when we can just count 1, 2, 3 boys, 1, 2, 3 girls. But when the sets are infinite, we need to use an idea like one-to-one correspondence. So what Cantor did is he showed that the natural numbers and the rational numbers can be put in a one-to-one correspondence. And that means that they have the same number of elements. Every rational number has a partner in the integer or in the natural numbers. Every natural number has a partner in the rational numbers. This is a very unintuitive conclusion, but there were even more surprises. Cantor next showed that it's not possible to place the rational numbers and the real numbers in one-to-one correspondence. So there are more real numbers than there are rational numbers. This also means that there's more than one infinite size. In fact, Cantor was able to show that there are an infinite number of distinct infinite sizes. There are links on the web page near this video to provide proofs of both of these unintuitive ideas. Now that setting is where the notion of space-filling curves comes from. Cantor went on to say it seems to be obvious that the number of points in the unit interval on the real line, the numbers between 0 and 1, and the points in the unit square ought to be different. Why? Because the unit line is sitting down here as a very minor part of the unit square. These are the points where the second coordinate is 0. So the unit interval is a proper subset. It ought to be much, much smaller. Cantor tried to prove that, and he failed to do so. Later mathematicians such as Peano and Hilbert and others were able to provide a proof that the unit interval and the unit square have to be the same size. One way to show that is to create a function that assigns to each point in the unit interval a unique partner in the unit square. If the function makes sure that each point in the unit square has a partner from the unit interval, then the unit square cannot have more points than the unit interval, because every point in the unit interval has a partner in the square, and no point in the square is left without a partner. But the unit interval is a proper subset, so it can't be larger than the unit square, and the conclusion is the sets must have equal numbers of points. Space-filling curves were a way of producing such a function. One such function was attributed to the mathematician Wacław Sierpinski, who was from Poland. He produced a family of curves, a family of functions, which I'm going to call S0, S1, S2 on up forever. Each of these curves uses up more of the points in the unit square. And as these functions approach a limit, which does exist, that limiting function completely covers the unit square. Now, it may hit some points in the unit square actually more than once, but the idea is that the unit interval gets mapped onto the unit square and covers everything. So they have to have the same size. Now, how did he make such a mapping? Well, let's look at just the first couple of curves. S0 is this curve on the bottom. Here's the unit interval. The function just takes the points between 0 and a quarter, 0.25, and maps them along this line segment. And the points between 0.25 and 0.5 get mapped along here, 0.5 to 0.75 on this bottom blue line, and then 0.75 to 1 up here. And so that's the curve S0. S1 looks like this. It starts at this upper point in the near the left, and we can see the shades. It maps along the top, down here, along the right, down along the left, up along the left, and back to the starting point. And this curve does use more points in the unit square than the previous one. Well, here's what the next few curves look like. This is S2. Here's S3, S4, S5, and S6. And what we notice is that we keep using more and more of the points in the unit square. And again, in the limit, as the subscript goes to infinity, we just end up with a solid square. So that's what space-filling curves are. But you might think about, how do I draw something like this on a computer? That seems rather difficult. Here's S4. And even giving instructions, we can see that each of these pieces are just little line segments. They're all the same size. Over here is a double line segment, two segments, one after the other. But providing instructions to fill in that curve just seems horrendously hard. Fortunately, there is a mechanism that allows us to do that. It's a programming technique called recursion. And using recursion, this is a fairly easy thing to do. What is recursion? It's a problem-solving strategy that uses the solutions to one or more smaller versions of the problem to create a solution to the original larger problem. Now here's an example which you might not have thought about using recursion before, but many of you are familiar with the Pascal's triangle. In this triangle, every entry is the sum of the two entries above it. So this 4 is 3 plus 1. 21 is 15 plus 6. 35 is 15 plus 20. Of course, we have to start somewhere, and so these ones down the two outsides are just given. They're what we call a base condition. We eventually get to a point where the recursive function knows directly how to find that. So if we think about how to produce this 6 in the middle, we know that 6 is the sum of its two parent numbers, but this 3 is the sum of the two numbers above it. And this 2 is the sum of the two numbers above it. And so we have to recurse and then recurse and recurse to get the pieces. And so we're using many smaller versions of the Pascal triangle to produce the sum for this one. That's the strategy of recursion. And here's how we can use it for Sierpinski curves. The Sierpinski curves actually are built upon 4 smaller recursive functions. There's a set of functions, A0, A1, and so forth, that fill in this upper triangle. Similarly, a B0, B1, etc. that goes to the right, C's over here, D's over there. And we successively fill in more and more. So I want to show you an interactive web page that allows us to fill in these curves. Here's S2, and down at the bottom is a little diagram that explains how to fill in S2. To make S2, it says first draw an A2. A2 starts at this point and moves around in this way. Then it says we end up at over here, and it says draw down and to the right. That's a single line segment down and to the right, and then draw a B2, which ends at this point. Draw a line down and to the left, and draw a C2. Draw a line up and to the left, and then draw a D2, and finally draw a line up and to the right, which lands us back where the A2 started. And so we draw an A2, a line, a B2, a line, C2, another line, D2, and the final line gets us back to the beginning. Now, just as in Pascal's triangle where we had to have those ones down the side, we define A0 to be do nothing. Similarly for B0, C0, etc. And so to draw S0, I start at the beginning point and draw an A0, which is do nothing. Then I draw a line down and to the right, draw B0, which is do nothing, draw a line down and to the left, do nothing, up and to the left, do nothing, up and to the right. To draw an A1, it says draw an A0, which is do nothing, draw a line down and to the right, B0, do nothing, 2 lines to the right, D0, which is do nothing, 1 line up and to the right, and then an A0, which is do nothing. Now remember what A1 looks like. To draw A2, we draw an A1, down and to the right, draw a B1. A B1 looks very much like an A1. Then do 2 lines to the right, draw a D1, go up and to the right, and draw another A1. So that's how to get A2. A2, B2, C2, and D2 are then combined using this diagram to produce S2. And we can do the same thing for S3. Notice one of the components of S3 is B3 over on the edge here. So that's how we can very cleverly draw these Sierpinski curves. And we can get things very complex such as this by just doing some simple recursion. If you're interested in how to do that recursion, there are links near this video that show you how to get to that, the notebook or the software that I use to produce this. Well, I hope you've enjoyed this video. I hope that you keep safe and that you keep studying and enjoying mathematics. And hopefully the next year's final contest will be held and you can all get together. Thank you.